Welcome back. In this lecture, we want to discuss instantaneous rate of change. We will see how we can estimate instantaneous rate of change of a quantity with respect to another quantity. So the first method of estimating instantaneous rate of change is called preceding or following intervals method. That's the name of the method. Now in this method, this is what we do. An interval of the independent variable of the form x in between a minus h and a, or x in between a and a plus h, where h is a small positive value, is used to determine an average rate of change. So I think by doing an example, this method will become clear. What is this preceding following interval method? So it says the size of the population of Armo City appears to be growing exponentially based on the equation modeled by P of t, that's again function notation, 42,000 times 1.04 raised to the exponent of t, where P of t is the number of people in the city and t is the number of years after 2000. Estimate the instantaneous rate of change in the population in 2018. That's what the question says. Okay, so we are going to consider two intervals, preceding and following. So first I do the preceding one. So preceding interval, what could it be? Well, it says t is the number of years after 2000. So that means t equals 0 represents the year 2000. T equals 1 would represent 2001. T equals 2 would represent the year 2002. And t equals 18 would represent the year 2018. So we can say, okay, t is less than or equal to 18 and greater than or equal to 17. We can select this so-called h value, that increment, to be 1 unit. So a is 18, and then 18 minus 1 is 17. So your independent variable x, or in this case t, is trapped in between 18 and 17. Of course, you could have selected a different h value. Instead of 1 unit, which I selected, you could have selected any other unit, let's say half a unit. So you could have said, for example, you could have said, or t is less than or equal to 18, but it's greater than or equal to 17.5 if you select that increment of h to be 0.5 units instead of 1 unit. So nobody says you cannot select that, or even a different value for h. You can select h to be 0.1 instead of 0.5. So if that's the case, then we're going to say delta p over delta t equals p at 18 minus p at 17, and then we divide by 18 minus 17. So if you do the calculation and plug in there using the calculator, you get 85,084 minus 81,812 divided by 1, which will give you 3,272 people per year. Okay, so this is one answer we get. So average rate of change of population with respect to time, it's going to be 3,272 people per year. But the thing is that, as I said, you could have selected a smaller h value, such as 0.5. So in that case, your lower limit or lower bound would be like closer to t. Instead of being 17, it will be 17.5. So in that case, the calculation would be the same, except that you would say p at 18 minus p at 17.5, and in the bottom you would have, of course, 18 minus 17.5. If you use a calculator and you do the math, you plug it in the equation for t, you would get 85,084. If you plug in 18 and then 83,432. And when you divide it by 0.5, you would get 3,304 people per year. And you see that these numbers are close to one another. 3,272 is close to 3,304 people per year. Both of these are estimations end of the day, and that's why they are close to one another. As the size of the preceding interval decreases, the average rate of change, as you see, it is increasing, right? So this interval from 17 to 18 was 1 unit, but from 17.5 to 18 is half a unit. So if that interval, we call it preceding interval, if that is getting smaller and smaller, what you see here is that the average rate of change is increasing. So that's an observation. So as the size of the preceding interval decreases, okay, the average rate of change actually increases according to what we found. From 3,272, we went up to 3,304 people per year. Now, this is for the preceding interval, but then you may have a following interval. So in part B, I'm going to select another interval, and this is the following interval. So this time I'm going to select t, which is greater than 18 and less than or equal to 19. So again, I'm using that increment of h to be 1 unit. It's this scenario basically. A is 18, h is 1, so 1 plus 18 is 19. So your independent variable x, in this case t, is trapped in between 18 or 19. And of course, as I said, you could have selected a smaller value for h, such as 0.5. In that case, I should say t would be greater than or equal to t less than or equal to 18.5. Or it could be 18.2 or 18.1, 18.01, depending on what value you select for the h, the increment h. So if we repeat the calculations delta p over delta t, we end up with p at 19 minus p at 18 over 19 minus 18. And in this case, again, when you plug in the numbers, you get 8,488 minus 85,084. You have to use your calculator and actually find these answers. It's not difficult to plug in for time t. You should actually do it. And we get 3,404 people per year is the unit. And then if we select that other interval, which was between 18 and 18.5, then in that case we have p at 18.5 minus p at 18. And if you do the subtraction, 18.5 minus 18, the denominator would be 0.5. The numerator would be 86,769 minus 85,084. As I said, you have to use the calculator and actually find these numbers. So 3,370 people per year is the average rate of change that we calculate. So now, in this case, as the size of the following interval decreases, the average rate of change decreases as well, because from 3,400 we went down to 3,370. So that's the observation here. So we're going to say as the size of the following interval, before it was preceding interval, now it's the following interval, decreases. So as we select a smaller interval, now we see that the average rate of change actually decreased, right? So decreases, and this is the observation that we can conclude. So now, the thing is that you are going to ask, okay, so after all of this, what is the final answer to the question? I know that all these 4 answers I got are just approximations, right? I could have even selected a different h value, let's say between 17.1 or 17.9 actually, and 18, I could find another estimation actually for the average rate of change of population with respect to time. But the thing is that you're going to say, okay, then end of the day, what should we say the final answer to the question is? Well, in this case, I should say we can make an estimate using the average of the two calculations for smaller intervals on either side of t equals 18. So if you recall, we said that we had two estimations before, and the one that was more accurate was actually 3,304. So we can grab that 3,304, and then for this other scenario, 3,370 was more accurate because we had a smaller interval between the 2 points. So geometrically speaking, the 2 points were closer to one another. 18.5 and 18 are closer compared to 19 and 18. So the secant line is closer to a tangent line, and the slope of secant in the second scenario would be much closer to the reality, which is the slope of the tangent line. So it is better to use this other answer, which is 3,370. So we selected one result from the preceding interval and one result from the following interval, and now we're grabbing those two and finding their average. So we just add them up and divide it by 2 to come up with some sort of final answer. So 3,337 people per year. Perhaps, if you agree, we can come up with this as a decent or final approximation for the instantaneous rate of change in the population in the year 2018. And 2018 is just 1 point. It's not like the average rate of change where we had 2 points. And we just estimated the instantaneous rate of change of population using this preceding / following interval method. And we found many estimations. All of them are okay, correct, but more accurate result in the preceding interval was 3,304 because we had a smaller interval. And if you had selected even a smaller interval from 18 to 17.9, for example, then you would have a more accurate result. And for the following interval, we selected 3,370 because we believe that's a better approximation. And so we grabbed those two and we found the average, and we came up with the final answer for the question for the instantaneous rate of change in the population in the year 2018. This method can be used to estimate instantaneous rate of change, and it's called preceding following interval method. There's other methods out there, mind you, and I'm going to discuss them in future lectures. These are just different methods of estimating instantaneous rate of change. That's what these are. Thank you.